All right, Unit 4, what is light? We're in Chapter 13. 13 is the start of the new unit, and of course we were talking about waves and sound in our last unit. We're talking about light here. Now, it's interesting to know that sound and light actually have some things in common. And when we're talking about light, we're also talking about waves a little bit as well, which you'll find out. It gets a little complicated with light, though, in terms of viewing it as waves or as particles. We're going to talk about that here, too. So, what is light? Sometimes science asks questions that seem obvious, but turn out to have much more complicated answers when examined. What is light is one of those questions. This is because we have dealt with light in our lives for so long that we assume that our familiarity with it means that we understand it. So there's a lot of things we take for granted, right? Most of us here have good vision. We can interpret colors and see motion and things like that. Sometimes, we may have glasses or something like that to help us see, which we'll talk a lot about glasses. We'll talk a lot about defects of the eye and things like that. That's part of this unit as well. But we don't really think about light and the nature of light all that often. But let's examine briefly the history of light. History of light. So I've got some of your blanks in your paper there filled out here for you, or highlighted anyways. History. So Plato and Socrates in ancient Greece thought that the eye emitted invisible light rays that reflected back to the eye, allowing it to see objects. So it was once thought that it was the eyes that generated these light rays. So there was energy coming out of your eye that actually kind of bounced off the objects that you were looking at. Yeah, that makes a lot of sense, doesn't it? Except your eyes don't work when the lights are off or at night, which is really strange. Your lights don't work. My eyes don't work when it's night. That's weird. I thought everything was coming out of my eyes. So a bit of a problem there.
Because we're solar powered, actually.
We're solar powered. Oh, that could be part of the, I don't think so. Pythagoras. You recognize him from math class, the Pythagorean theorem. He was a mathematician and philosopher of the highest rank, and he thought that light particles bounced off an object and then into our eyes, allowing us to see it. Okay, so very similar, but that the light didn't originate from our eyes, that light came from, like the sun, or lamps, or things, the fire, things like that. So Pythagoras kind of shifted things a little bit. Aristotle, in the 4th century BC, thought that light traveled like a wave in water. So Aristotle, obviously a giant of a mathematic and scientific philosopher himself, thought about the nature of light quite heavily and thought, hey, I think that light is behaving like a wave so much, not like, these sort of enigmatic sort of light rays. There's some wave property. Question?
He was a giant.
Yeah. Leonardo da Vinci in the 1500s. Leonardo da Vinci in the 1500s, the 1500s, also thought that light had wave-like properties and was similar to sound. So as we move through, and Da Vinci obviously was 2,000 years later, looks like here from Aristotle, but the connection between light and sound started to be made there. So in the 17th and 18th centuries, the debate between whether light was a wave or a particle began to be tested. So in the 16 and 1700s and into the 1800s, experimentation, right? The Enlightenment, experimentation, new developing thought. Dalton. We'll talk about Dalton in chemistry, I guess, maybe a little bit more. But experimentation started to be a thing, like back in ancient Greece. Right? Experimentation was not relied upon because they didn't have good instruments. There was too many factors, and you couldn't isolate just one thing because there's so many things happening at once. And they relied more on just the purity of thought and reason. So when instrumentation and just the experimental method started to develop, then more experiments could be done and more data was collected, and it was, science developed quite a bit there. And so the idea that wave was acting like a particle began to be tested. So obviously a wave would be just sort of this, mush of energy, but not really an actual thing. And of course, a particle would be like a rock or an eraser or something, right? That actually, strikes something or has, even like some quantifiable, package, right? So it's like, is it a wave? Is it sort of like a sound wave that we can't really grab onto? Or is it like tiny particles that if we could see small enough or zoom in far enough, maybe we could actually identify these little packages of energy? So that's kind of the discussion that started happening then. Isaac Newton, you've probably heard of him. Isaac Newton developed a strong theory of light as a particle that explained the bending of light, that's refraction, and reflection, and color. So Newton contributed much to light, as well as James Clerk Maxwell, which isn't on this list, but electromagnetic spectrum and waves, and that was developed further. And I like James Clerk Maxwell. I think he was a relative of mine, actually. My dad's name is James Maxwell, actually. Yeah. And Uncle Jimmy here. I call James Clerk Maxwell Uncle Jimmy. We'll find out more about him later, but he's from Scotland, like I am, and has the same name as me. And looks like me, actually. To be honest with you, I've seen pictures of James Clerk Maxwell. He's got the same nose as me. Profile. It's actually, yeah. Well, maybe a little later. Yeah, maybe a little later. But we don't really study Maxwell's equations in this class, so I don't have them on the list. But it is worth a mention. But we do study a lot of reflection and refraction, the bending of light, just like we talked a little bit about the reflection and refraction of sound waves, right? A little bit. All right, Christian Huygens in the mid-1600s showed mathematically that a wave could also demonstrate these phenomena. So again, connecting waves, particles, reflections, refractions, and waves, all of this started to be developed. And again, we're just running through a quick history, some important names of scientists that contributed to the sort of the modern theory. Oh, here we go. Uncle Jimmy is on this list. Great. Thomas Young, in 1801, does the famous double slit experiment showing that light definitely has a diffraction pattern. And again, we will dig into some of these things a little bit, but not all of them. So the double slit experiment, we won't talk too heavily about. But light does have a diffraction pattern, kind of an overlapping of waves, causing neat things to happen. Augustin Fresnel, or Fresnel, I guess, it really should be pronounced Fresnel, develops a comprehensive mathematical wave theory of light. This is in the late 1700s. And here's Uncle Jimmy, James Clerk Maxwell, in the mid-1800s, developed a very robust mathematical set of formulas that explained how light was formed due to electrical forces acting within the atom that produced a wave called electromagnetic radiation. And to be honest, most of the equations of most of his work is too far above me. I wouldn't even be able to give you a detailed explanation of everything. It's pretty amazing stuff. But a lot of the technology that we use today, a lot of the experimentation and a lot of the developments today came from his work on light as well. So electromagnetic radiation, or ER, has frequencies between 10 to the 1 and 10 to the 25 hertz. Visible light is about 10 to the 15 hertz. So visible light that we can see in all the colors actually have a wavelength. They actually have wavelengths. So light as a wave is very well established, and again, the nature of some of these things, we still don't have it completely figured out. What you have to understand is that in science, we come up with a model and we say, what we see seems to fit this kind of model. If we think of it like this, then we can explain what we see, and we can predict things about the nature of light. But these models that we make are limited somehow because we're finding out new things. It's like, hey, that doesn't fit the model, so we have to change the model, or there's developments that come along. So that's the neat thing about science. That's also the tough thing about science, is you think you can have things figured out, and then somebody does an experiment. It's like, hey, that doesn't seem to fit. So what are we missing? And so you always have to constantly adjust, your scientific theories. But so when we talk about light as a wave, there's a lot of things that we see, and a lot of things that light does that fits into that model. But also you'll see that we can treat it like particles, energy and light, as actual physical particles. So it's a bit of a duality. It's called the, anyways, we'll get into it. James Maxwell's theories, very strong, has allowed us to develop things like radar, microwaves, radios, lasers, etc. So here's the question. Is light, when I say it, I'm talking about light, is it a wave? So it's a wave. Unfortunately, light also behaves like a particle does at times. And so our model of being exclusively a wave sometimes doesn't fit. Because, like I say, sound is different than this eraser, right? I can shout at you and you can kind of go, oh, that hurts my ears. Or I can throw this eraser at you and hit you in the eye, and you can say, oh, that really hurt my eye. There's the nature of those two different things are pretty different, right? So who wants to volunteer? I'll shout really loud at you, then I'll chuck this no, I'm just kidding. We had some hands. We had some hands go up and we had some finger pointing. That's not very nice, okay? Yeah, throw the eraser, yeah. Anyways, okay, you ready? Are you ready? Keep your eyes open, don't blink. Oh, you blinked. Oh, too bad. See, that wasn't sound or the eraser. That was just your own fear. Wow, now we have a third dimension. Ouch, it's getting more complicated. Okay, so this means that scientists have to say that we truly don't know the exact nature of light. We might call it a wavicle. And yes, I made that up. Fully particle and fully wave at the same time. A wavicle is not a real thing. Actually, I think Mr. Reed might have even made that one up, but anyways. A wavicle. A wave, particle, wavicle. That should be, I should patent that. We should patent that word. That is definitely an RCS word, wavicle.
Do you have a song for this section?
Do I have a song for this section?
You didn't give us a song about the last one.
Oh, I didn't do the ear song. I'll do the ear song for you sometime too, yeah. I was trying to remember it the other day. It's been a few years.
So,
Do I have, you know what, I should make up some kind of song for the history of light here, shouldn't I? I should include all these scientists or something like that.
A verse about MathWell.
Yeah. Okay, I'll work on that. Maybe that's coming. Yeah, and a verse totally dedicated to Uncle Jimmy. Exactly. Uncle James Maxwell. Okay. Wavicle. When you're walking down the street, if you pass me, just give me a little wavicle. That means you wave at me and throw something at me. There you go, at the same time. Hi! Okay, wavicle. All right, so we don't fully understand what light is, but we have a good idea, and we can study and use these sort of models or this merged model to examine properties of light. Okay, awesome. What about the speed of light? Let's move into 3.2. The speed of light. How fast is light? Well, we know it's faster than sound because lightning shows up in the sky before thunder reaches us. We talked about this, right? If you're playing baseball and you're out in the outfield, you see the batter hit the ball before you hear the crack of the bat. When you shoot a gun, okay, you're in a race, you shoot a gun, you actually technically see the puff of smoke before you hear the sound, although it's really quick. But if you're far enough away, you can see things happen before you hear that same thing happen. And that difference means that there's a difference in the time it takes for the light to get to you. And we'll talk a little bit more about light here real quick, but it's not anything that comes from your eyes. Your eyes just don't all of a sudden not work at nighttime. So it is external light. It's light bouncing off objects, and that your eye perceiving that light that's coming into your eye, right? So light travels really fast, sound travels slower. That's the difference in what you see and what you hear are the same thing. Yeah, question?
Light is a wave. Would that mean it would make a sound?
If light is a wave, does that mean it can make a sound? It's not something that we can hear. Like our ears wouldn't be able to hear it. But so then that comes that question, does it make a sound, right? What's a sound? I guess, what's a sound? Is it emitting a frequency? Then yes. If it's us being able to perceive and differentiate between those frequencies, then no. Because you can't really,
light doesn't have
yellow doesn't sound different than green. It just kind of looks different than green.
But
So.
light doesn't have mass, so how would it interfere with the air to make sound waves?
So light doesn't have mass, so how would it interfere with the air to make sound waves? Again, energy, right, in the form of, like anything in the form of energy doesn't have to have mass, like a heat or, energy, right? Yeah, you're right, it doesn't have mass, so how can we hear it? It does emit a frequency, so this is good. We're talking about a spectrum, right? There's certain frequencies that we can hear that disturb the air. I mean, is my voice an actual tangible particle? Right? Does my voice have mass, right?
No, but I mean, like your vocal cords do.
Yeah, so does light excite the air molecules? I guess that's what you're asking, right?
Yeah.
So, okay. These are good questions. These are good questions. Let's keep thinking about those questions as we move through the notes here. Is it instantaneous? Is light instantaneous? Does it travel at an infinite speed, or does it have an actual speed, do you think? Well, infinite speed, I don't know, instantaneous, that's a little tough. You might think that it's instantaneous. There were many reasons to think this for a long time that it was instantaneous, though. It's just so very fast. Also, you cannot see it move in our everyday life, so one might think, oh yeah, it's just a thing. It's instantaneous. Only when observing things really far away can you start to notice the lag that is produced by light. Now, when I say lag, I mean the kind of delay, right? So Olaus Rømer, a Danish astronomer, noticed this while observing the eclipses of the moons of Jupiter. So I have a little diagram on the right here that you can kind of see. So we have Earth over here on the right, closer to Jupiter. We have Earth over here on the other side of the sun and the other part of its orbit, quite a bit further away from Jupiter. So this is a setup to this question. At one point of the year, when the Earth was on the opposite side of the sun from Jupiter, it took longer for the light to reach the Earth. Therefore, listen carefully, the eclipses appeared later than their calculated times. So we knew a lot about how, the moon revolves around Jupiter, and, when we should be able to see the moon come around from the backside or whatever. But at different times of the year, those calculations were off a little bit. Okay, so what was witnessed had a bit of a delay. Okay. When the Earth was on the same side of the sun, the eclipses appeared earlier than predicted. So to account for the difference in distance between Jupiter, so distance 1, distance 2, obviously what was the only factor that was different? Well, it was the light that was coming to us from Jupiter to be able to observe this. So there was no indication that the moon actually slowed down or sped up at different times of the year when we were on different sides of the sun, so it had to have been the light. So that was one of the things that kind of made people think, okay, this is a very long distance, so if light is super fast, we wouldn't be able to see a difference between, within the Earth or within any, maybe experiments we could do here, but if we're talking about the distance between Earth and Jupiter, there's quite a difference there, and so we might be able to see something.
Right.
Yep.
How did he figure this out? Because
So on page 413, you have actually two diagrams sort of what I've drawn here in the notes. The Jupiter one, and then beneath here, Albert Michelson, late 1800s, did an experiment to calculate the speed of light. And what this involved was a light source. So a light source over here shot a ray of light. And what happened was there was this octagonal 8-sided mirror that was spinning around very fast.
you know if it's going the other way. That man.
What? Just let me finish, okay? Just listen, please. It might be helpful if you put your hand up if you have a question, okay? That would be very helpful. Light source shining on a octagonal mirror, and the mirror is spinning very fast. So you can actually figure out what the light bounces here, and then it reflects to another mirror that's 35 kilometers away. So it says here 35 kilometers. 35 kilometers away. It takes some time to get 35 kilometers, even though light's really fast. But then it has to come back to this thing. So that's 70 kilometers now that this light has traveled. So I think, well, 70 kilometers. You're driving for, like, from here, about 3/4 of an hour away you're driving, and that's how far, that's almost back to where I grew up. My farm where I grew up is about that far away. It's about 85 kilometers away. So, you're driving for about 3/4 of an hour, right? That's about how far the light has to travel. So if you think about this little mirror, and even if there's only, like, if there's a mirror on one section of this, and I think that's may have been how it was set up, a rotatable mirror. Anyways, and so when this thing spins, right, if you change the speed of how this thing spins, you can time it so that this light ray that goes to the mirror and then comes back hits the mirror as it spins around over here. And you can actually vary the speed of this thing, and you can figure out, okay, I need to have some kind of uninterrupted, light path, light beam, and then when it's received over here at like a telescope or something, you'd spin this thing, and so it'd be like, no, I can't see anything, and then all of a sudden I see the light beam. So the difference in rotational speed and kind of where this position is to this position, they could kind of figure out how long the light basically took to get from the mirror, first of all here to this mirror and then back again. So there was some measurable time, and they could figure out that time was super small, like just like a fraction of a second, but it still is some time. It takes some time to get from here and then go 70 kilometers and then back here. So that sort of thing, you can read a little bit more about it on page 413, but that kind of an experiment where they're talking about a large distance and a very small measure of time, the scientists were able to figure out what the speed of light was to a pretty precise degree. So we are going to go with, again, this is rounded, but it's 2.999 something or whatever. I think you see in a lot of publications, but 3.00 or 3 times 10 to the 8 meters per second. So we've mentioned this before in class. It's 300 million meters per second. Okay, so obviously 300 million meters is far greater than 70 kilometers, right? That's 7,000 meters. So it would take far less than 1 second for all this to happen in this experiment, right? But if we're talking about, the light having to come from Jupiter all the way to the Earth on the other side of the orbit, we're talking about millions of kilometers there. So that actually is fairly measurable. Okay? How long does it take light to get from here to Jupiter? Well, it depends where here is. It depends where here is. Like, is here, or is here over here on the other side of the sun? So there's a bit of a difference. But you could probably look that up. You could figure that out. What's the distance, even like right now, from Earth to Jupiter? And you would, use the speed to find the time.
But the light would be going from the sun off Jupiter.
Right, but the light that we see would be reflecting from Jupiter. So if we're looking at Jupiter, we're looking at light rays that have come, from Jupiter. So what you could find is how many seconds ago the light that we are now seeing from Jupiter, how many seconds ago that light actually left Jupiter, right? So, and like from here to the sun, right? From here to the sun, it's about 8 minutes, okay? So what's that, 480 seconds, 8 times 60? So 480 seconds. The light that if we were to look up at the sun real quickly, right, or the light that we see on the ground during the day, that light actually left the sun, 8 minutes ago. So it does take time, and we know that now, for the sun to travel. All right, there are questions in your textbook. I would like to pause now and give you some time to work on questions 1, 2, page 414. Just talks about light, the speed of light, just a couple calculation questions for you. So that's 13.1 and 13.2. So take a few moments to work on those questions. Okay, grade 11s, just so you guys know, you'll see this in the textbook, and you'll see this everywhere now. The speed of light, the letter or the symbol for speed of light is a lowercase c. Okay, so that's the speed of light. So when you see in the sample problem on page 414 there, and I would encourage you to look through that sample problem. That's an example of what you're doing for those two questions. But V equals C equals 3.00 times 10 to the 8 meters per second. So the V is the velocity of C, which is representative of the speed of light. So remember that velocity equals distance over time, or more specifically, the change in distance over the change in time, right? But speed or velocity equals distance divided by time, and time, of course, equals distance over velocity or speed. So just a couple notes there as you work on those questions. There. So question number 1 says, light from the planet Uranus takes 242 minutes to reach Earth. That is a time, right? So remember, write down what you're given, write down your formulas that connect your givens and your unknowns, okay? So light from the planet takes 242 minutes. So that's a time that you're given. 242 minutes. Calculate the distance from Uranus to Earth. Okay, so distance we don't know. What else do we need to find out, or what else do we need to use in order to solve this problem? Speed equals distance divided by time. So we're trying to find distance. So distance equals speed times time, right? What's the speed that we're talking about here in this question? Sorry? Yeah, it's the speed of light, right? So this is actually speed of light, and that's going to be in meters per second, right? What is this time in? It's in minutes. So do we have a problem there? Yeah, we do. We can't just multiply those or divide those or whatever. So we need to put this minutes into what? Into seconds. Then you can see that those will cancel off and you'll just get a distance in meters. Okay, so that's how you do number one. Number two, you guys asked about elapsed time. So that's just the time that goes by. So a radar pulse traveling at the speed of light is sent to the moon. So from Earth to the moon, right? After being reflected, it returns to Earth. So it has to come back to Earth. This whole time is 2.5 seconds. So the time elapsed is 2.5 seconds. How far in meters is the moon? Well, D, we don't know. And V or S, the speed is, your speed of light. So there you go. Okay, give you a few more minutes to figure that out. Yeah, so depending on what units you put your answer in, there's going to be, if it's in meters, then it's 4.356 times 10 to the 12 meters. And if you put it in kilometers, then it's times 10 to the 9. Okay, so speed equals distance over time is where you want to start with. Solve for D. Okay, make sure your units line up. Minutes have to be converted to seconds. And for number 2, again, define the total distance of 7.5 times 10 to the 8 meters in this question. Factors into the fact that the light is traveling to the moon and back, so you have to half that distance to get the distance from the Earth to the moon. Okay, so for 1 and 2, any questions? Any more questions about that? All right, so those are probably the easiest math questions you're going to get in this class. It's just a simple speed equals distance over time, manipulating this equation. You have to know how to do that. So if you have any problems with that, if you don't know how to solve for D here or how to solve for T here, then you need to come talk to me afterwards, okay? If that's still a problem for you.